All right, you made it to the final review. So I've linked a little page here to help you with C++ syntax. So this will go over like all the way from like functions up through inheritance, like the entire C++ language, a review of the syntax. That's what this page has. And you should be able to understand pretty much all of it now. You've made it that far in your C++ journey. And then, of course, we still have plenty of data structures and algorithms to go over. And by the way, data structures and algorithms are pretty much the most popular thing that appears in an interview for a company when you go and you like try to get an internship or finally a job after you graduate. So just to make things silly and fun and to keep myself sane as I was writing this review set of slides, we're going to imagine that you are in for an interview at this magical company that is a conglomeration of a bunch of big names. And so enjoy the absurd little comments at the bottom there. So the first thing that I want to go over is stuff that has been covered in the first 2 midterms, stuff that I've already tested you on, but like we just keep building on top of it. So I am not going to let you forget it. So we have to go over that first. All right, so let's do that. Let's talk about just ADTs, abstract data types. That's what that stands for, right, in general. And the difference between those and data structures, all right, because that was a big deal at the start of the class. So let me fix these pens first. Boop. There we go. So remember that a data structure, that's a way of structuring data, right? It's a concrete idea of how the data is looking inside of the memory of the computer, all right? So it's like, if you have a data structure, that means you know exactly what the values in memory look like and how they relate to one another, okay? So like, whenever you see the word data structure, you should think like, I know what's going on in memory, your memory. Like you can draw a picture if you needed to. Like, all right, this data structure looks exactly like this in memory. I've got an int here, and I've got an int pointer here, and that pointer points to this int like that, and like got another pointer here that goes like that, and this thing maybe wraps around in some weird way. It's like you can draw these diagrams. That's what it means for a data structure. I know exactly what's going on in memory, how big all these boxes are, all that fun stuff. Okay, so that's data structures. Linked lists, for example, are a data structure. Like I know that each node consists of a data piece and then a next pointer to some other node. All right, so each individual node takes up what? This is 8 bytes for a pointer plus 4 bytes for an int, so that's 12 bytes total, something like that. You should be able to say that on the top of your head. All right, so that's the idea. That's what data structures are all about. And data structures are used to implement abstract data types, and so that's like the other side of that coin. There's a big disconnect, but they are related at the same time. So abstract data types, or ADTs, that's like the idea of a type. It's a mathematical model of it. It's like a black box. It's defining a type in terms of what it can do for you, in terms of behavior, in terms of operations. All right, so it's just a black box. You have no clue how it's implemented. The representation, that's a data structure problem. The ADT itself is just like, I know how to do pushback. I know how to do .at. So like a vector, for example. Before we learned how to build our own vectors, we treated vectors like a black box. Like, all right, whatever a vector of ints is, I don't know. I can't see through it. All a vector of ints is something that I can like ask to do things for me. I can say, hey vector v dot pushback. Right? You're giving it commands. That's what an ADT is all about. Pushback 42 or something. And then that's a void method, so it's like, sure, I'll do that for you. No exceptions. And then as long as like it plays the game of a vector correctly, like .at of 0 now gives back 42, like then it is a vector for all intents and purposes. You don't care how it's implemented. It could be a dynamic array like it is really in real life, but it could have been like, you could have used a linked list to make this vector happen, as long as you implemented these operations correctly. All an ADT is whatever its operations say it is. All right, but you use ADTs to implement data structures, backwards. You use data structures to implement ADTs, and so they reference each other, right? Every abstract data type has some underlying set of data structures that create it, okay? So that's the secret, and that's the difference, all right? A lot of the data structures we talked about in this class were made on the heap, which is a lovely, lovely place. We can't forget about that either. So let's see, when you're making just normal variables like ints and stuff, like most of the variables you made before you took this class were like, they were local variables. They were inside of a function. They were stored on the stack, all right? So the stack looks like this. It's all the memory that belongs to the local variables for all the functions / methods you call. So like maybe main has some variables, and then you call a function and it deals with some other variables. Okay, so there's another function call, like it's got its own little variables. Those things live on the stack and they go away when the function's returned. Okay, that's in contrast to a magical place called the heap, right? We love the heap, and it stores dynamically allocated memory that you create whenever you want to. All right, it's allocated on the fly. You say new, then the name of a type, and you get back a pointer to that type made on the heap for you. All right, so let's say we did this in main, int star I equals new int. What that does, the second you run this line, like there's a box called I in main, let's call that one, there's my I right there, and it will get, right, it will get the pointer to a brand new box in memory that we make. So you say new int, and you can also give a value, actually. You can say what should go in it as well. New int, maybe 42. That'll work as well. So what that does is that makes a box on the heap that holds 42, capable of holding one int. It's got an address, like 100 or something, and it's shiny and new. And that is our dynamically allocated memory. That lasts for as long as we want it to last until we say delete, okay? So that's that. And so if you say int star I equals new int on in main, then I is a variable, it's a local variable that points to this brand new place on the heap. So I will hold 100 and point just like this, okay? So that's the beauty of this. This box lives forever, even if like you made it in some other function and like it returned or something. As long as the program's still running, that heap memory is still there until you say delete, okay? That is the beauty of it. So it lives forever, at least until you say delete or delete bracket bracket if you want to make an array of things, okay? So that T can be a normal type like an int, or it can be a type that you've made, like a class, like counter, or even string, like whatever you've made, it's fine. That's okay. You can also make an array of things, an array of some other smaller type U, okay? So yeah, maybe you can pass it along into other functions and work with it. Or those other functions can also make stuff on the heap. Like you call a foo function for main, it can also make stuff on the heap, just like that. And hopefully, by the time foo is returned, you're either returning the address of this so you still have it and you don't leak memory, or you delete the thing. Because that pointer is going to get chopped off the second. You're going to lose that pointer the second the foo function returns, and you might leak memory accidentally. Okay, so if you lose access to something without deleting it, that is a memory leak. And so local variables, they go away when functions return. We have to clean up after ourselves. So like, how do we clean up after I? Once we're done with I, we better say, it's just one thing, so we'll say delete. Delete without any brackets. Delete I. Okay, and so that'll go there. Go to address 100, whatever's in I. Go to that address in heap memory and get rid of it, reclaim it, okay? So yeah, that's the heap in a nutshell. I know you've used it a lot in this class, but it's good to see another drawing here and there. So there's that. Some other stuff that we've already tested you on are stacks and queues, okay? So this is a very nice ADT example, right? Because we know how to implement stacks and queues using linked lists, but the ADT version of them is just like, all right, I can push, I can pop, stuff like that. Okay, so here are the operations. They're ADTs, you know, because they're defined in terms of these operations. So a stack you can push, get the top, pop, see if it's empty, and then queue is pretty much the same, but it's like front. You get the front rather than the concept of a top of it. So yeah, let me draw some of those. Again, these are usually implemented using linked lists, and let's see. Yeah, I think that's what I want to say for now. So let me draw a picture and then we'll talk about the acronyms. So a stack, if you push to a stack, like let's push 1, then 2, then 3 to a stack. 1. So now this is the one and only thing. That's also the top of the stack is the one and only element, the 1. Okay, so I've pushed 1. Now I've pushed 2. Now I'll push 3. All right, so this is the top of my stack right now. All right, top. If you push, you add to the top. Okay, so let's say that I push 4. Whee! So it's like the idea of pushing 4 would add it right here. So push adds to the top of your stack. And then pop also removes from the top. So you're always working with the top one way or another. Okay? So if you were to pop the stack, the idea of popping it, I'll use a dashed line again, popping a stack removes from the top. pop removes from the top. So you can always only access the top of the stack. All right, that's what a stack is all about. It's LIFO for that reason. Last in, first out. The last thing you push onto the stack is the first thing that's coming off of it when you pop it. Okay, so that's that. Queues, similar. Let's push 1, 2, 3, 4 to a queue. So a queue works like this. So like the empty queue, it's like a bunch of people waiting in line, right? So if I push 1 to an empty queue, then it's the one and only thing. When you push to a queue, you add to the end. It's like a person getting in line. Okay, so I push 2, it adds to the end. So it goes 1, then 2. 1's at the front, 2's at the end. Then if you push 3 to the queue, it's always to the end. 1, 2, 3 in that order. And so if you were to, the idea of adding one more thing, pushing like 4 to the queue would add it here to the back. Okay, so that's where it would go. Push adds to the back, or the rear, some people call it. And then popping, this is the difference between stacks and queues, is where you pop. So if you were to pop the queue, it would remove the very first thing, the person that's waited the most patiently. Okay, so pop removes from the front. And that's the only difference between stacks and queues. Pop removes from the front. That's what makes a stack and a queue, where you pop. So queues, we say, are FIFO. The first thing that you put into it is the first thing that you're getting out of it when you pop. Okay, that's the opposite of stacks. Okay, so a good example problem, a silly example, is technically this is used in compilers, is balancing parentheses. It's a syntax error if you forget to balance your parentheses as you're making function calls in C++. So let me show you a cool little algorithm that will check and see if a string that has just parentheses in it is correctly balanced. So like if you made a weird function call foo with some inner arguments, like what does it mean that this string of parentheses is balanced? Like dun dun, is it actually balanced is the question. Maybe that's balanced, 1, 2, 3, 1, 2. That may very well be balanced right now. Balance, and then like that. If somebody gives you all that, like was it balanced or not? That's useful knowledge if you're making a compiler. All right, so the algorithm it's going to end up using a stack is to determine whether a string of parentheses is balanced. You're going to push to your stack whenever you see an open paren, and pop whenever you see a closed paren. And if you ever try to pop when there's nothing there, it's not balanced. All right, and if also there's not, and also if there's something left at the end, it's not balanced. So here's the algorithm. All right, so you're going to push every time you see an open paren, and then you're going to pop whenever you see a closed paren. All right, and so here's my example. Let's work through this one. Let's say that this is my string of parentheses and it is not quite balanced, right? It's missing one at the end there. So let's kind of walk through what's going to happen, okay? Or maybe let's add it in. Let's watch what will happen if it was actually balanced, okay? So these strings of parentheses, they are balanced right now. And so what we're going to do is we're going to start a stack, a parenthesis stack, and we're going to go and we're going to run our algorithm from left to right on all the parentheses in this string. So every time we see an open paren, we see one, we're going to push it. So push open paren right there. Push it again because we got another one. And then every time you have a closed paren, it's meant to like cancel out one of the old ones. So that one's going to pop the stack. Every time you see a closed paren, it's supposed to like line up with another one, so it pops that one off. Does that kind of make sense? And then this one, it should pop the other one off. Okay, and then now we're back to nothing. Do you see how that's going to discover balancedness? That's pretty cool. It's a cool use of a stack, I think. And so I think you can understand now what's going to happen if I didn't have it perfectly closed off. So all right, let's push this one, right? That's what the algorithm's going to do. Now we got 2 parentheses to close, right, that have not yet been closed. We're going to close one, so we pop the stack. And then do you see how we're left hanging at the end with one unclosed parenthesis? Just like the nature of a stack helps us and notices exactly when we aren't balanced. That's kind of cool, right? So that's a simple algorithm to discover balanced parentheses. And so like if we did have another one here, we would have popped it off and the stack would have been empty at the end. All right, so if That's kind of your algorithm. You check what it looks like at the end now. So if the stack is empty at the end, this is a great idea, or a great example to code up yourself. Try it. I highly encourage it. If the stack is empty at the end, that means your string of parentheses, or like function calls, or whatever it really represented, then it was balanced. Everything will work out. Beautiful. If it wasn't empty, like this example, if it wasn't empty, if I could spell properly, or if you had something like this was your entire string, you'd just be trying to pop an empty stack all day long. If you tried to pop an empty stack, then like there were no open parens that needed to be there. Does that make sense? So if it wasn't empty at the end, or you ever tried to pop an empty stack, then there was something was unbalanced. Okay, you tried to pop an empty stack, then for one reason or another, it was not balanced. This one means you were missing some closed parens, and this one means you're missing some open parens. I hope you see that. Okay, so it's a fun little example of the usefulness of just a stack. Like these 4 operations, they're pretty nice. All right, when they're all you need. When they're all you need. Okay, so yeah, I think that's what I wanted to say for that. I have a cool little example of iterators now. Okay, so I want to talk about iterators because those go hand in hand with all the data structures that we kind of talked about. So C++ made iterators for us for a lot of types, like vectors had iterators, lists had iterators, maps have iterators. Every C++ container has iterators inside of it, begin and end, those things. So let me show you how to make your own, okay? And then that'll let it be like accepted by the range-based for loop. You remember that? The for loop with a colon inside. So let me show that to you, okay? This is very similar to Python in a sense. So I would like to go to some code now. Got some pre-made code here for us. There we go. It's called iterators.cpp. So I've made a little iterator for us. All right, it's a range iterator, the kind that Python has. Let me show it to you. Oops. That'll make some more as well. So here's the idea. Like I want to be able to range through a bunch of numbers. All right, I'd like to iterate through from 1 to 5, let's say. So I'm going to make a class called range that like keeps track of where I am within a range. Like the idea of wanting to range through the numbers 1 through 5. Okay, so I'm going to make a range type and an iterator for the range type. So like I can do r.begin, r.end, all that fun stuff, and like advance an iterator with the ++. You know the syntax, and then the star works, right? All that stuff. If I do that, like I want it to print from 1 to 5. Does that make sense? That's what I'd like to have right now. Yeah, remember that an iterator, just in general, an iterator, you kind of think of it like a pointer. It's just a class that remembers where you are inside of something, okay? So like usually you think of iterators as like going through vectors or something. So like your iterator, your IT iterator, it starts at like v.begin or whatever. Go until, as long as you're not equal to v.end. You kind of think of it as like it's got a little pointer inside of where it is, right? And you say, you can advance it and be like, all right, star IT gets the thing that's in there right now. Star IT will give me the thing that's in there, and then IT++ will advance it to iterate to the next thing. Okay, so that's kind of how we think of iterators. They're like kind of like pointers. All right, iterators. So look up the documentation for like the vector iterators, the list iterators. They are classes that store. It's a special type, right? It's just an object, right? All an iterator is, it's a way to remember where you are in something. Are classes that store where you are in some bigger piece of data, like a data structure. all right? But in general, all you need to be an iterator, all you need is to be able to get made with a dot begin, to like know where you end with a dot end, to be able to plus yourself, right? To be able to dereference yourself to see where you're iterating to right now, and then to be able to compare against like the end and make sure you're not there yet. So you don't need equality check, you need disequality check actually. So as long as you implement all these things, you are an iterator. C++ can kind of understand you, all right? And we get some free syntax based out of that. So like I'd like to be able to range between the numbers 1 through 32. So I'll make a range type that if I say dot begin and dot end, it tells me like where I am in the range, and like as long as I can advance it and check for it properly, like that'll work. All right. So that's kind of what I've done here in this range type. So all a range thing is just a way to hold on to where we are. It's a place that knows the start and the end. Okay. So that's pretty much it. Like that's all you need to store a range, right? You just need to remember where you are right now. Where are we and where are we going? Where are we? Like you start at 1, and then you go and when you do ++r, right? Then it will be 2, then it will be 3 if you ++ it again. Like that's what I want to be able to do. That's what my iterator should be. Okay? That's the goal. So there is a difference between the range itself and an iterator to it. So I made actually 2 different types. So let me split screen this. So here down at the bottom, I have made a range object. Like I want to iterate from 1 to 5, and I want to do this kind of iteration with it. So like I want to be able to go from like the beginning of the range up until the end of the range, and like advance it. For a weird reason, I'm doing ++it instead of it++. That's just how the operator is going to work. So don't worry too much about it. It's going to be okay. And yeah, r.begin and r.end will give back a range iterator. All right, so our range just knows its start and end. All right, that's all it's doing. And then the begin and end, just remember where we are. Okay, so a range iterator is just the idea of like, where am I right now? What is the number I'm looking at right now? Does that kind of make sense? I hope it does. So like, okay, if I have a range, an iterator through my range, like here's where I am right now, I'm at the 1. If I advance it with the ++, I get to the next thing, the next piece of the range. So like that's my one piece of data, is like where I am right now. Dereferencing it gives me what I'm at. So like *r shows me like *r gives back the 3 or whatever I'm at right now. And yeah, just want to be able to advance it to the next one. Not equals check is just like check if the thing inside is not equal. It's like my where are we? Is that not equal to the others where are we? So do you kind of see how those will all go together? r.end here will return an iterator to 5. r.begin returns an iterator to 1. As long as 5 is not equal to 1, because that's the kind of comparison we're doing, then like keep going, use the iterator to print out the 1, the 2, the 3, the 4, the 5. Eventually we'll get to 6, right? Because the end is 1 plus the start. 1 past the end, right? It's always 1 past the end. Then we're done, all right? And so let me comment out most of this, like the rest of this, and show you that working. Because that's all it means to be an iterator, just the idea of going through something. So this is just some fancy code to print from 1 to 5. There's the first one, that's the second one that I use. And the beauty of doing it this way, like to have these types involved, like they have to be exactly called begin and end, and the ++ operator, and the not equals to operator on your iterators, and the star operator. Once you have all of those, like that's all you need. That's what all the C++ types are doing, like all from the standard library. They unlock this ability to use the range-based for loop, because that's all it's doing. It's going through and using iterators secretly. Okay, so I've implemented all these for my new range type that lets me use this style of syntax. This code for every I in my range R gets turned into, and like do this with it, gets turned into this code up here. All right, so this is a great file to study to kind of understand finally what's going on under the hood of an iterator. Okay, so yeah. Do you see how that's also going to print from 1 to 5? It's going to turn it exactly into this. It's going to figure out the types and, all right, start the beginning, go until the 1 past the end. As long as you're not there, keep on advancing through the range. And that'll do it. Isn't that fun? So that's what it means to be an iterator. I love it. So I will also give you an example of like, all right, how do you actually make a vector iterator? Like, what's going on in the standard library? How are they doing that? All right, so there are plenty of ways to make an iterator for a vector. You could actually use pointers. One idea, here's one that I'll be doing, is let's make an iterator for vectors by holding like a reference to the actual vector or a pointer to the vector somehow. Give me that vector in some way. Call it v, because the iterator needs to know where that vector lives. Like, where's the beginning of it? Whee, so something like that. There's my vector. And do you kind of understand that, all right, if I want to know where I am in the vector, one way to do it is just like to save what index I'm at. That's one way to make an iterator. Like, all right, what's my current index in the vector? Oh, it's 0 right now. So that means that's my star operator. If I overload it, just like go to the vector at index 0. Does that make sense? Like, you can make your own iterator now for any type, as long as you have that in mind. And then like IT++, or really plus IT, because you kind of have to do it backwards, with the operators the way they are, will advance, right? Will advance the index. And so like when you do star IT again, it'll go to the vector at index 1. You can just save where you are in the vector like that, by saving where it begins and then what index you're going inside of it. And of course, 1 past the end would be an index of like size plus 1, or sorry, exactly size. I hope that makes sense. Okay, so let me show that to you. So here I am. I made a vector, and then I made a custom type called vector iterator. Vector v's dot begin and dot end, they're already returning the normal iterators from the actual standard library. So I just had to make functions like vector underscore begin, vector underscore end to give back these vector iterator things that I can then like overload the operators for and let them do what I want to do. So here's what it means to be a vector iterator. It's like I need a way to know where I am in the vector. Give me the vector, so like a reference to it, and that works. And then an index where I am at in that vector. Okay, so like just go here at index this, and that's your star operator. Okay, so yeah, to create it, you got to set these member variables. To do the star to like dereference your iterator, to go to where you're looking at right now, just like, all right, I got my vector and here's my index in it. Go there. To do plus plus is just advance the index that you're looking at. You're at index 0, go to index 1 now. Okay? And then not equal to, technically this is kind of cheating, because maybe you should be checking like, are these the actual same vector? But we'll just pretend that we can never mess it up. So like to be not equal to it as an iterator is like, just make sure that the indices are different. Okay? And then the beginning and the end of your vector, it's like, all right, the beginning of a vector is an iterator to that vector at index 0. The end iterator is like, all right, an iterator to the vector at index size, because that's 1 past the end. Size minus 1 is the last index. Size is 1 past the end. We never want to go there. So as long as we're not equal to that, we can do the star and advance and keep going. See that? And that's suddenly a new kind of iterator to a vector. It doesn't actually involve pointers. So cool. And here it is. It's working. And that's more or less that. It'll do the right thing. So you can make an iterator for any type you have. And if you do it with these kinds of names, and like it is a class at the end of the day, and you do it with these kinds of exact names, then the range-based for loop syntax will just work and get translated into a use of your iterators. Isn't that cool? And you can also overload the standard library's iterators if you want to do it this way. But then you got to use the full syntax. I think it's very magical. Like, or I guess, depending on how you think of it, it's slightly less magical now because you know the secrets. You know what's really happening. All right, so that's the concept of iteration, right? That's what an iterator is all about, a wrapper around that. So cool. Custom iterators, we know how to do that now. So yeah, that's just a piece of syntax that I wanted to teach you one day. It's a good review of C++. So, all right, now let's talk about complexity. So big O is like the letter we like to use when we're analyzing algorithms for like worst case. But really remember that when anybody's asking you for big O, like in real life, because big O just means upper bound, really what they mean is big theta. It's easier to say, oh, fewer syllables, right? That means tightest bound. So if I ask you on a test, give me a big O analysis, I really mean big theta. That's just what people are use to mean that, okay? So big O, or big theta, or big omega, they're just notations that tell you the asymptotic growth of a function. Like a mathematical function, it tells you how fast it grows It's like an approximation of how fast it grows, all right? And so that the reason we care about that in computer science is we can give a mathematical function that kind of correlates with how much work is being done inside of each of our algorithms. So we can associate a mathematical function of like basic operation counts to all of our algorithms. And so that's what we care most about. But mathematicians made this first for their own stuff. And yeah, you can do a bunch of different kinds of analyses of algorithms. There's usually, worst case is the one we care usually the most about, because like how, in the very worst case, when nothing goes our way, how fast is this thing? But you can also think about the best case analysis or the average case analysis. Like on average, if I do this operation, how much time will it take? How many operations will it take? So yeah, as far as big O is concerned, here's the actual mathematical definition. Like here's the picture to go along with it. The mathematical definition of like, all right, I have a function with a variable n. F of n is big O of g of n, or for short we say f is big O of g, and you write it like this in full mathematical notation if these two things are true. Or sorry, I guess the first thing is true. But technically this one is equivalent to the first thing. So if there exist constants c and n naught such that for every n greater than or equal to n naught, the function, your original function, it is bounded above by g at the same input, but scaled by that constant c. So as long as you're going later than n naught, like it all works out. So like your function, like here's f, and here's your scale g of n. You pick that c to make it work, and then f of n might not be correctly approximated by c times g of n for a while, but eventually at n naught, from then onwards, it's always above. C times g of n is always above for the same input, f of n. And so it's bounding above, all right? F grows no faster than g with this appropriate constant tacked out in front, all right? And so that's big O. If you want the tightest bound for big O, then what you do is you drop the lower order terms. This will give you big theta, really. If you do your counting, if you have you have your function ready to go, if you drop the lower order terms, the ones that don't really matter as n gets large, or whatever your input variable is as that gets large, you drop all those guys, and then also any leading constants, because you're going to put a constant out in front of the other thing anyway. It doesn't matter. And leading constants don't matter either. So if you drop those guys, here's kind of an analysis. Like, all right, I know that my function for a given n, it takes this many basic operations, 7n squared plus 17n plus 42, and then we can analyze that. Like that, okay. The lower order terms are these guys, get rid of them. That's just 7n squared. And then any leading constants we don't care about. Like 7 is just a constant. So my analysis is this is big O of n squared, because you could find an appropriate n naught and then some constant, probably like 8, right? That eventually this times that constant wins out, all right? That's what you mean, all right? That's how you do big O analysis or big theta analysis, okay? So go back to the book and to the previous slides. There's also big omega and stuff like that. Know them all, but we care the most about big theta in this class, even though we say big O when we mean big theta. So just remember that. All right, that's going to be true for the rest of your computer science career. People say one thing and mean another. All right, so yeah, there's two different kinds of complexity that we care the most about analyzing in this class. It's running time complexity or runtime complexity, as well as space complexity. So let's talk about both of those. All right, so running time complexity, if you had to pick one, running time complexity is the one we care most about. So we really like time is money. We care how long it takes to execute an algorithm for some input. Like I do not want to take all day to compute this number I need, all right, to perform this action that I need to count. To do. So yeah, the way that you determine runtime complexity, the way that you solve for it, is you count the number of basic operations in your algorithm, okay? And so do you remember how to do that kind of thing? It's on the order of the number of lines of code, as long as they're not going to like call other functions or do any fancy looping things. But like for example, go back to the slide where I first talked about this, but like inside of a CPU, like if you're running this one line, like how many basic operations does that take? Like what do you actually have to do inside of a CPU? Well, you have your two variables, you have to compute their sum. That takes a basic operation, and then like returning takes another basic operation. So this takes like two. It's a constant number of basic operations essentially for this line. So that's kind of how that works. And so yeah, let's go through different kinds of common complexities and talk about them. All right. So constant complexity O of 1 is constant time. That's like a very quick thing. You can't do any better than that. It's one of these. Right. If you sum 2, 3, right? That's this line, isn't it? If you make a function called sum and you give it these two values, like into x and into y, like there's one line as your body. It's this. You're doing two basic operations. No matter how big these two numbers are, they're both still ints. And it takes a constant amount of time to add two ints and return the answer back inside of a CPU. Okay? So that is what constant time is all about. Logarithmic time is the next fastest. Like constant is as good as you can do. Logarithmic time is still very fast, but slower. A good example of logarithmic time is binary search. So remember that binary search works like this. It starts out like you've got an array and you're looking for something in it. Like I want to know, you've got a sorted array, first of all. It's got to be sorted. And you're looking for a value in that sorted array. And the way that you can do it is using that like guess the number game strategy, where like you always check in the middle first, because it's sorted, you know you have very strong guarantees about what's to the left and to the right of you. So at the start of time, your search space is the entire vector or array. You haven't looked at anything yet, so you look in the very middle of that. And you're like, all right, how does this compare to what I'm looking for? And then like, oh, the thing I'm looking for was bigger, so I'm going to search over here. And now that's I have a half the size search space. And I'll go and look in the middle of that. And like, oh, okay, the thing I was looking for was smaller, so I'll half the search space again. So in the worst case, you're going to half your search space. You're going to chop it in half. How many times and still have something to look through? Well, it's on the order of the logarithm of the number of elements, number of original elements. So you can only like take a log, you can only chop your search space in half log of n times, if n is the size of the vector, and still have something to look through. That's your worst case analysis. Because you could have like found it right here. That could have been your best case analysis. It was in the middle. But in the worst case, no matter where it is, it will take like about log of n searches, log of n basic operations to go and find the thing. Okay? So that's logarithmic time. Linear time, a good example of linear time is linear search. So that's, I've got a vector or an array, and I want to look through everything because it's jumbled, and I have no clue what's where. If you got a jumbled array, the thing that you're looking for could just as easily be at the start or the end or the middle. It could be anywhere if things are out of order. All right, so yeah, that's linear search. Something a little bit worse is n times log n, and that's merge sort. A good example of that is merge sort. So like you're trying to sort through some stuff and you're going to do a recursive merge sort algorithm. Like you've got your original vector, and what you'll do is you'll chop it in half. Two jumbled arrays, they're out of order right now, and then you recursively merge sort them. So like this is now sorted, this is now sorted, it's increasing order. And then like you're going to do that a bunch of times. You're going to keep chopping it in half and sorting it, and then eventually like merging it back after it's been sorted. But like this process to get down to the base cases, you're chopping your vector in half. How many times can you do that? What's the height of this recursion tree? It's log base 2 of n. Let me draw that in a way that you can read it there. And then you got to all build it back up. Okay, so like you do linear work at each level, and so it's n log n. All right, so go back to like your book for the full analysis of that. But that's n log n. Takes a little bit more time than a linear search. And then n squared, a good example of n squared is like you're drawing a box of stars on the terminal or something. Anything that involves nested loops. So like for I equals 0 to I equals 1 to n, let's say, like that's one loop, and then like you've got something nested in between because nested loops multiply their work. And it doesn't have to be exact, right? It could be like I equals 2 to like n minus 1. That still counts. It's pretty much n squared, right? You're doing your analysis, but it could be exactly n as well. So whatever this body is, if it's constant work in the body, it's being multiplied n squared times. And so O of n squared for like a doubly nested loop, and it gets worse for more deeply nested loops. N cubed, right, for a triply nested loop. That's disgusting. So that's running time complexity in a nutshell. Go back to these examples and kind of think about them and like how they compare. All right. So next is space complexity. What's the difference between running time complexity and space complexity? Whereas running time was about like how long does it take to run this code, space complexity, excuse me, is like how much memory is involved as you are running your algorithms. All right, so it's like what is the number of bytes on the stack and the heap being used by my algorithm when I run it? Okay, it's like think of it this way: how much stuff do you need to store based on? Usually, it's based on something like some variable, like the size of your input. Okay, so yeah, for example, if you call a function, like all right, I've got this function foo, and I want to do the space analysis of it. What's the space complexity of foo? Well, if all it needs are like a couple parameters that are ints and like a helper variable or something, that's only what, 4, 8, 12 bytes of stack space regardless of my inputs. And so that's constant space. If you just have a constant number of variables that hold a constant number of things. So this gets worse if this is like an array or something. You have to make an array that's of a different size. Like that changes things. But yeah, if it's just a bunch of constant size variables, and it's always the same number of them, that becomes constant space. Yeah, so it's really just like count the number of bytes in a sense, count the number of variables you're using, the number of ints that you have access to or are creating. The real thing that I want to talk about before I switch slides is recursion, because recursion kind of messes up your space analysis. It makes it harder. So with recursion, remember that you're calling yourself. Your own function is getting called a bunch of times. And so like you've got multiple calls all running at once, and all the ones underneath are paused and waiting on the person above them. So you have to include all of the stack, all of the calls to your own function that could possibly be running at once in your analysis. All right, because like each recursive call is going to grow the stack, and it's going to add new space for like the parameters and all the local variables for each call to that function. Okay, so essentially what you're going to do is you're going to like figure out the space complexity of a single function call, and then also figure out like what's the worst case number of recursive calls that could be stacked. Okay, so like a good example of a recursive function is like factorial. So like you got main that calls factorial or something and asks for 4 factorial. And so you've got like a variable involved, right? You've got your parameter, you got space at least for that, and maybe like some helper variables or something, but at least a space for a 4 variable. But even though you might have constant space being used at each call to your recursive function, you're going to call yourself a bunch of times. Like 4 factorial is going to call 3 factorial. Well, 4 is still running, right? It's got to figure out the smaller factorial, and that's another parameter saved on the stack. You see that? And then 3 factorial's got to call 2 factorial. These are all waiting on each other, so these are all running at once. So you got to remember that, okay? And then 2 factorial will call 1 factorial to store 1, and then like the base case is 0 factorial. Eventually we get to here, and this is the worst case number, right? It's the average case and the best case too, I guess. Like you're always going to get down to this. So all right, what is the space complexity of a recursive factorial function? Well, you've got like n plus 1 calls going at once, which is O of n still. O of n calls to your recursive function, and then each call, as far as factorial is concerned, takes up how much space? It takes up constant space. Taking up O of 1 space. Because it's just like a variable and maybe like a temporary thing as well. You got your parameter and like a temp variable. And so like you multiply those, O of n times O of 1, that becomes linear space complexity for a factorial function. And so don't let the fact that, oh yeah, just one call is constant space fool you. You have a bunch of calls all running at once, okay? And you're just counting your own call. Like main doesn't count in this case. Okay. Just the thing you're trying to analyze, you count. So that's space complexity. What else? Yeah, let's just keep on trucking. Let's talk about hashing now. Hashing and hash functions. So if you have hash functions and hashing, that lets you use a very fancy kind of a lookup table, essentially. All right, so hashing lets you use an array or a vector as a lookup table for any type. if you have a hash function, it will give you an index, okay? So any type can be the key type for your hash table as long as you make a hash function for it, all right? So the goal of any hash function is to take that type, like a string or whatever, that I want to use as my key, turn it into some large non-negative number, because that kind of number can be shrunken down and used as an index of my lookup table, all right? That's the name of the game for hash tables. It's what you want to be able to do is insert key value pairs and look up things based on their key, look up values based on their key. All right, so the standard example is like a phone book, right? You're asking for, you got string keys to int values. That's a phone book. And so you can't just like use a vector because you can't go to an index that is a string unless you have a hash function. All right, so yeah, let me just kind of have an idea of that. Let's say that we want to insert this key value pair, like, all right, mom maps to mom's phone number. I don't know, 555-5555. Okay, that's mom's phone number, and that's like an int. Okay, so how do you do that? Well, you've got to make a hash table first, space for all this. It's a table of key value pairs. And then you also need to worry about, like, okay, what kind of collision handling am I doing? Am I doing open hashing or closed hashing? Let's say we're doing open hashing, all right? So you've got indices 0, 1, all the way to boop, boop, boop. This is your table size -1, -1. And, all right, let's say that I want to insert mom mapping to this, so I need to come up with an index to place mom. Right? Where will mom hash to is my question now. So I make a hash function that takes a string to a non-negative number, all right? Turns it into an unsigned int. That's what we need to do now, okay? So, all right, I have some hash function on strings, and I call it with the string mom, because that's what I want to find an index for. And let's say that that gives me back somehow like 227. That's my fancy number. And maybe that's way bigger than the size of my table. So what I'll do is I'll take this number and I'll shrink it down, all right? You can turn it into an index of your lookup table. A very easy way to do that is with the modulus. So I'll take my 227 and I will mod it by my table size. And that will give me a number between 0 and table size -1, which is a valid index. Isn't that perfect? And let's say that that ends up being index 1. And if we're going to do open hashing, then at each index, we're going to store a list of key value pairs. So like, all right, maybe this is the only thing here right now. So it's a list of size 1, and the only thing there is the pair mom. You got to store the key and the value. Mom mapping to the number 555. Da da da. Okay, so that's open hashing in a nutshell. So you're just like taking this type and figuring out an index involving it. So I can use this array is like an array that's indexed by strings in a weird way. That's what hash functions are all about. And hash tables allow you to go and quickly look up the value now that this is in here. I'll just hash mom again, get to index 1, look through this until I find the key mom, and then give back the corresponding value. Okay? So hopefully this is all coming back to you. Do yell at me in office hours or something if you have any questions about this stuff. But yeah, we're just doing lightning round review for all this, because technically you've seen all this in a previous exam as well. So, okay, let's go next to binary search trees. So BSTs for short. What can you do to a BST? Well, you can look for something that's in there. You can insert new stuff. You can remove old stuff that's already in there, hopefully. And then there's also a bunch of traversals on your binary search tree. So a binary search tree is a tree that is arranged in a very special way that kind of like mimics binary search. Remember that. So there's an idea of order and sortedness. So a binary search tree, all of the nodes reflect and respect the binary search tree property. So like if this is my root, it's the 5 node, then everything to the left is going to be, like this entire subtree has got to be smaller than 5, and everything to the right and this subtree's got to be bigger than 5. And that's true for every other child as well. All right, so let me fill in the tree, and then we'll draw that again. So let's say 3 can go here, but like 6 cannot go here. All right, and same like over here, like 8 can go here, but 4 cannot go here. It's not allowed because it's only bigger things can go over there. And I can put a 1 here because it's smaller than 5, and 3, And then I can put a 4 here because it's smaller than 5 and bigger than 3. All right, and so here is like 8. I can store like a 13 here. That'll work. And so yeah, that's your binary search tree property. Like this entire subtree, because 5 is the parent, everybody over here has got to be less than 5. And everybody over here has got to be greater than 5. Usually you don't use in a binary search tree equal things, but you can also pick a side if you want to add duplicates as well. Like this is the less than or equal to side, and then it's okay. But usually you don't deal with duplicates. And then that's also true for everybody else. Like everybody to the left of this 3 is also less than 3, as well as less than 5. Okay, everything from the outer one also applies. And everything over here is greater than 3, but also less than 5. So that's very much constraining what you can put there. Do you see that? It's very important. And then like this one, by going here, it means, all right, yeah, I got to be greater than 8 if I'm going down this side, and also greater than 5. I guess this one overpowers that one anyway, but you get the idea. Okay, and all of this is true for these subtrees. Like, all right, all these guys over here less than 3. All these guys over here greater than 3. Strictly less than 8. Or sorry, greater than 8. Excuse me, greater than 8 over here. So that's what it means to be a binary search tree. To search a binary search tree, in the worst case, you're going down to like the lowest leaf, which is the height of the tree. Insertion as well. You kind of like you're searching for where it could have gone. Like if you want to insert, I don't know, 3.5. So you might get down to the lowest leaf and have to add a new leaf underneath that. And so that's, again, going down the height of the tree and doing constant work once you get there. Removal, again, height of the tree. We'll remember the disgusting removal algorithms, but I believe in you, okay? Also height of the tree, though, because you got to do like predecessor or successor, and then in the worst case, in that 2 children case, and then do some swapping and some constant work after that. But height of the tree to get down there and to do like the predecessor or the successor in the worst case. Okay, so there's also traversals. Don't forget those, and like every other recursive thing, pre-order, post-order, in order. There's also breadth first. So just don't forget those. I'll give you an example later, but let's walk through each of these. So let's say I want to search. So let me have an example tree. That example tree, let me redraw it. This is the root of my tree. Got 5, and then 3, 8, 1, let's do 4 and 13 again. And I'm going to use this as an example for pretty much for a couple slides after this. So let me just keep on copying and pasting it. Give me a second. Let's do one for insert, one for remove, and then I guess predecessor. We're going to need that one. I think that's all. Good enough. All right. So let's do search. So you want to search a binary search tree for something. Well, first you need a value that you're looking for. Let's say the value we want to search for is like 4. And so starting at the root, you're going to start a pointer there and compare what you've got, what's at your current node, to what is the value that you're searching for. And if you see something bigger than what you need, then you need to go left, right? If what you're looking for is smaller, go left, because that's the only place it could ever be, right? Go left, and then if it's bigger, you go right. If it's equal, you're done, right? You found it. And so, all right, I'll start at the root. 4 is smaller than 5, so I'll go left. Boop. And then I got 3 versus 4. 4 is bigger, so I'll go right. If it's anywhere, it's to the right. And then I'm here, all right? So I went left and then right, and I made my way down here. I found it, all right? So there's the 4, and we can return that we found it or something like that. And the analysis, right, in the worst case, you've gone down the height of the tree, all right? You've gone down the height of the tree, which is the lowest leaf. This is level 1, 0, 1, and then this is 2. So you went down 2 edges to get there, and that's as far as you could have gone. That's the worst case, the height of the tree nodes. I guess the worst case is you're looking for something that's not there, and so you get to a leaf, and then you'd go one more time, I guess, technically, but that's still O of H. It's just H plus 1, which is still O of H. I like O of H better than O of N, because in the worst case, technically, if your tree sucks, if it looks like this, then technically, if your BST looked like this, it really was just like a linked list, then your H is N. But I feel like H is just a better idea. It's like, all right, if you had a nice tree, H is smaller than N. So I think H is a better idea when we're doing our analysis. But O of N is technically also correct, and so some websites will say that because you could have a tree that's ugly like this. All right, but I like O of H. I would prefer it if you said O of H in this class. Okay, so that's search. Yeah, height of the tree. Insertion, let's do that. That's pretty much the same as search because like it starts with a search. All right, so let's say I've got this tree and I want to insert a new value. I want to insert the value 11. All right, so the first step is like make sure it's not already there because like you don't want to insert something. You don't want duplicates usually in a BST. So it's search for the thing, and then the search process will take you to where it would have gone if it were there, because usually you're not going to find it, right? Because you're inserting it. You want to put something that's not there, not yet in there. So you're going to search for the thing. So again, starting at 5, I'll go right because 11's bigger. I see 8. I'll go right because 11's bigger. I see 13, 11's smaller. And so I'll go left and, okay, there's nothing left. So this is where it would have gone if I could have gone left, and I couldn't because there's nothing there, this has got to be the parent, right? 13's got to be the parent. You're just going to insert it where you would have found it, all right? So, yeah, all you got to do is like, okay, make this node, put the 11 in there, make the node on the heap, right? So, like, what's the time complexity? So it's constant to make that new node on the heap. Set the pointers, right? Set the left pointer of the parent and the parent pointer of the child. Like that, right? You got to do both of those things, and that's constant work. The searching process, though, getting down potentially the height of the tree to get to where it would have gone, where is its parent, that is that's the bottleneck. All right, so it's O of h time to get to where it would have been inserted, and then it's O of 1 to like do the actual insertion. So it's just that plus that. So O of h total again to do the insertion because it's both of these guys. You add them up. Okay. So that's insertion. Let's do removal. All right, so you got 3 cases, and only one of them is the hard one. Okay, so let's say we've got a leaf and we want to get rid of it. All right, so that's case 1. If you want to remove a leaf from your BST, that's super easy. All you got to do, let's say we hate the 4 node, we want to get rid of it. All you got to do is go to its parent, find its parent, and chop off the fact, like, okay, it was a right child. Get rid of that right child, set it to null or something from its parent's perspective. Just do that. That's constant work, right? And then also, of course, delete the node. So that's still constant work in case 1. Just make the parent forget about it. That's easy, okay? Case 2 is slightly harder. If you have a node with 1 child that you want to delete, it's still not too bad, all right? So let's say we want to delete the 8 node. What do you do in that case? Well, what needs to happen is eventually this node goes away, but before you get there, its parent and that 1 child that it has need to become linked. So 8 was the right child of 5, so the right child of 5 needs to become that 1 child. So you need to do that, all right? And that lets the parent forget about it, all right? So you make that 1 child the child of its parent, and then the parent of this child now is no longer 8 because we're about to get rid of the 8. So you also do the same thing for the parent. Like it becomes the old node's parent, all right? And then you're ready to delete the node. That's still a constant amount of work, all right? So you just reset that parent pointer as well. And it's not too bad. So those are the 2 easy cases. You do have to worry about maybe changing the root, so you do have to like have some special checks and things because you may have changed the root in those 2 cases. But still not too bad. The last case is the hard one, though. All right. So if you have 2 children, let's say we want to delete the root or something. We want to delete the 5 node. What we will do, all right, you are forced to use either the predecessor or the successor, right? So let's do, I guess, the predecessor as this example. Successor's also going to work, right? So let's do predecessor. What you'll do is you'll find that thing, you'll swap the keys there, and then the key that you want to delete is now at a different place. It's in one of the places that is case 1 or 2, and that makes it much easier, all right? That's guaranteed to be one of the 2 easier cases because that's what it means to be a predecessor or a successor. You can only have max 1 child. Otherwise, you could have found something bigger or smaller. All right? So, all right, let's say we want to do predecessor. I want to get rid of the 5 node. And so I'm going to go find the predecessor, which is, it's go left and go right forever if you can. So go left once to get the 3. And then there is nothing because we got rid of the 4 already. So like the 3 is the predecessor. And so I want to swap the 3 with the value I'm trying to delete. All right, so I'm going to swap the 3 and the 5. Technically, you don't have to put the 5 anywhere. It's just like this is the node I'm about to delete anyway, but it's okay. So we're going to put the 3 at the root now. So this node is actually not going to be deleted. We've just put a new value there. We've like thrown off the problem of deleting this node to somewhere else in the tree that only has one child now, right? Because we've gotten rid of this guy. So, okay, then this becomes a one-child case. Do you see? It's just like, all right, just hook those guys up like that, and you're done. It's like, then you can delete this node. It's easier that way. All right. So I hope that makes sense. And yeah, we found that that was our predecessor. So it also works for the successor. It is symmetric, and it's going to be one of those cases. And then once you have this node, this new node that is your predecessor to delete, you can make a recursive call to deletion. That'll end up being a base case. These two are your base cases. So really, this is a recursive algorithm, surprisingly, though the recursion will only last for one round. And so you don't have to worry about this horrible space complexity. It's never going to blow up like this. It's only going to call itself once to get to a simpler case. And that's nice. That's good on us. All right. So yeah, let me zoom in on the predecessor and the successor algorithms just to give you the full detail of removal. Let's do predecessor again. Let's say I want to find the predecessor of let's do the 5 node first. Okay. And so the idea of finding the predecessor of something is I want to find the thing that comes before me, right? The biggest smaller thing, essentially, if that makes sense, okay? So if you have a left child, that means, all right, the things to the left of you are smaller. I want to find the maximum smaller thing. So I'll go left once and then go right as far as I can. Boop, boop, and that leads me to the 4 node, all right? So there's my predecessor. That's how you find it if you do have a left child. So that'll work. That'll be fine. If you don't have a left child, though, let's say we want to find the predecessor of we want to start from the 13 node, let's say. We want to find the predecessor of the 13 node. Then, if you do have a predecessor, it's got to be one of your parents. It may not exist, but it's got to be one of your parents if it does exist. All right? So what you do is you go up until you find something that's smaller than you. And this time we only had to go up once. And so you just keep following parent pointers until you find something with a smaller key. All right? If you try to go up too far, like you go past the root, and you still don't find something smaller, then you just don't have a predecessor. You were the min of the tree, okay? But usually it'll work, unless you try with 1 or something. Like you keep going up, you never find anything smaller than 1, you get to the root, and then you're done. So 1, okay, that was the min in the tree. There's no hope for a predecessor. So yeah, that's how you find predecessor, and it's going to be O of H either way. Either you might have to go up the height of the tree or down the height of the tree in the worst case, okay? So I think that's what I wanted to say there, and that makes removal O of H, because, yeah, this is like the predecessor and successor is the bottleneck in case 3. So in the worst case, it's O of H to do that, and then constant work to do one of the other 2 cases that it turns into doing, okay? So yeah, that I think is what I wanted to say for removal. I think the last thing that I want to talk about today is just recursion in general. I'll give one example, and have you think about a different example. I think I'm going to stop in between, though. That's what I've apparently promised myself. So, like, we'll think about trees next time. We'll do recursion on just normal numbers, and then I'll do recursion with actual trees next time. So, okay, let's do recursion on numbers. Recursion, just in general, remember, is we had a problem, and we want to go find it inside of itself. We're solving a problem in terms of itself, in terms of smaller versions of itself. That's important, all right? So a nice hand-wavy reason for why recursion works is the following. When you have a recursive algorithm, you're going to create 2 things, a base case and a recursive case, right? So here's why recursion is magical and it works. The base case is kind of like you shouting out to the world, hey, for my problem P, I know how to solve it for its smallest version. I know how to solve P of size 0. That's my base case. You ask for P of 0, I know the answer immediately. I can give you that back without any extra work. So that's what your base case is doing. It's shouting out to the world, I know how to solve P of 0. If you ever ask me, I know the answer. All right? And then that works together with the recursive case, and this is what the recursive case is doing. It's like, all right, if, it's asking an if-then question. If you give me the answer to a 1 smaller problem, P of n, then I know how to build for you the answer to a 1 bigger problem, P of n plus 1. That's what the recursive case is shouting to the world, all right? And that's what you're doing in your recursive algorithm, right? You're making a smaller call to the next smaller problem, and you're using that to successfully build the 1 bigger version of the problem's answer, all right? So these two taken together, they give you a way to solve p of whatever you want, p for any n, right? Any n bigger than or equal to 0. Because say you ask for p of 5 or something. Well, you can just start at p of 0, right? You have that at your fingertips. I know the answer concretely to p of 0. And then you run the recursive case all day long. It's like, all right, set n to 0. Like, all right, if only I had p of 0, I could build p of 1. Oh, hey, I've got p of 0. I'll plug it in, and it will spit out, the recursive case will spit out p of 1. You see that? And then now I have the answer to p of 1 at my fingertips. I can run this rule again all day long, set n to 1. If somebody gave me p of 1 and I have it, I know how to build p of 2, and like, okay, feed it in. Feed it in, it will spit out p of 2, the answer. You see how it's going to build, starting from the base case, is going to build up the answer to what we need. So p of 2, you can plug that in, again, for the recursive rule. Like, okay, if somebody gives me p of 2, I can build p of 3. That's what the recursive case is claiming. We have p of 2, feed it in. Get out p of 3, get out p of 4, all the way to p of infinity, right? That'll always work out. And so if we really wanted p of 5, we will eventually make our way there, right? We'll eventually make our way there. When we're actually programming this, though, usually we start with the original call, and it makes its way down to the base case, and then it unwinds and works its way back up to the answer with the recursive case rules. But in general, in math at least, this is why recursion works. You just assume the smaller call works, because, like, assume you have that. As long as you build up the next bigger answer right, it really will make its way to the base case and correctly build up the answer. Okay? So let's do factorial, because that's like the quintessential example, just to show it all to you. And then we'll do like a fancier example on trees next time. So here's factorial. So this is a recursive problem. We need to first notice that. It's like, all right, we'll do some examples usually. And so we'll do like, all right, 5 factorial. What is that? Can I find a smaller factorial inside of 5 factorial? And then you'll notice like, oh yeah, there's a 1 smaller factorial, there's 4 factorial, as well as others, like 3 factorial, 2 factorial, 1 factorial. They're all there, but there's 4 factorial at least. And that's going to be, if you generalize that, that becomes your recursive case. Just like in general, if somebody asks me for n factorial, that's equal to my n times n minus 1 factorial. All right, so that's your recursive case. That's what that turns into. That's supposed to be an n. I'm not sure if that's legible, so let me fix that. N minus 1 factorial. So there it is, a bigger factorial defined in terms of a smaller factorial. That's exactly what it means to be a recursive case. All right, and then you also then go looking for a base case. Like, when can I stop this work? Because we don't want it to be an infinite loop. We want to eventually stop, and so you kind of just run your recursive case rule until it stops making sense. That's a good way to find a base case, usually. So like, all right, 5 factorial, that's equal to 5 times 4 factorial. Does that make sense still? Yes, that totally makes sense. That checks out. That is mathematically correct. And then, all right, let's break down 4 factorial. Let's use the recursive rule with n equal to 4. 4 factorial, according to my recursive case rule, is equal to 4 times 3 factorial. That still checks out. That's still fine. Okay, what next? 3 factorial, according to my recursive case rule, is equal to 3 times 2 factorial. Yeah, that's still fine. 2 factorial is equal to 2 times 1 factorial. Yeah, that still makes sense in terms of math. 1 factorial, all right, running my rule, that's equal to 1 times 0 factorial. That is technically fine. That is totally okay, because 0 factorial in math is defined as 1. It's defined as equal to 1 in mathematics. So that's still okay. Nothing is, like, the world is not blown up yet. That's still fine. All right, so I don't need to stop yet. 0 factorial, if I run this rule on it, well, okay, 0 factorial according to my recursive case is equal to 0 times negative 1 factorial. And this is where the world stops making sense, right? So in addition to 0, like multiplying by 0 makes the whole answer 0, also negative 1 factorial does not exist. It's not defined. And so we need to stop before we get to here, all right? So that means, all right, the last time this made sense was 0 factorial. So that can be my base case. That's kind of what you notice. Like, if anybody comes asking for 0 factorial, I'll just tell them the answer is 1, and then they can go away. Like, I don't have to do any more work with my recursive case. Like, I just know the answer immediately. It's at my fingertips. There's my p of 0, my smallest answer. There's my base case. I'll get to here and start building everybody else up from there. Okay, so that's the goal. And so that turns into code. Let us code that up together. Just quickly, I will call it just recursion.cpp. And yeah, let's call it fact int n, and it'll return the factorial of some number n. So like we want to print out fact of 5 or something. And so the goal is like, all right, I've got the code, I've got the recursive case, the base case, and to translate it, I just need to like do an if statement. Like, which one am I in right now? Am I in the base case or am I in the recursive case? So the difference is what I'm trying to take the factorial of. Is it 0 or something else? So if it's 0, I'm in the base case. If n is 0, somebody's asking for 0 factorial. And I know that is 1. That's my base case. So I'll just return 1 to whoever called me. Otherwise, I'm in the recursive case, right? I know in the recursive case, just in general, n factorial is equal to n times n minus 1 factorial. And then how do I compute that? Like, I need to return my n times, I need to compute n minus 1 factorial, but oh no, I'm the one who computes factorial. It's a smaller call. As long as it's a smaller call, I get to assume that I get the right answer back. As long as I build up the full correct answer, it really will be correct. It really will have given me back the true mathematical n minus 1 factorial. I get to call myself. Believe in the magic of recursion. So there, this will really give back n minus 1 factorial. Just assume it will. As long as I build up the right answer and have the correct base case, it will work out. All right? And so 5 factorial, I believe, is 120. I've done this example too many times. I've memorized the answer. So I do see 120 there, and just to prove that to you, let's go into Python real quick. I do get the right answer. Cool. So, all right. Let's draw a stack diagram for why this is working, just to convince you if this was too hand-wavy, this drawing and these ideas. So let's draw a stack diagram to once and for all prove to you why this is going to work out. All right, so main called fact of 5. Main is going to call fact of 5. And then, all right, fact of 5 is like, all right, I'm not 0. 5 is not 0, so I need to go to my recursive case. I'll return my n times fact of 4, but I don't know that answer yet, so I need to go off and compute that. So it's going to go, and fact of 5 will be paused on this line, waiting on this call to complete. I need fact of 4 before I can return something. So fact of 5 will call fact of 4. All right, I hope that makes sense. And now both of those are running at once. Fact of 5 is waiting on fact of 4. Fact of 4 is now, all right, with n being 4, still not 0. It's got to return its 4 times fact of 3. So again, fact of 4 is going to wait on this line. It needs fact of 3 in order to return its final answer and to compute it. So fact of 4 calls fact of 3. And then now we're in fact of 3. These are all running at once, right? Everybody's waiting on fact of 3 right now. 3 is not 0, so we're in the recursive case again. It needs to return its 3 times fact of 2. So again, it needs to pause right here, compute fact of 2, because it can't multiply its 3 by something it doesn't know yet. So fact of 3 is going to call fact of 2, and I think you get the idea. Fact of 2 is going to call fact of 1. Fact of 1 is still not the base case. Fact of 1 will try to return its 1 times fact of 0, so it needs to go off and compute fact of 0. It needs that answer. So everybody's waiting patiently on fact of 0, which is finally the base case. All of these calls, all these other lower calls, they're waiting on this line, on this smaller call to complete. And it's finally about to unwind. So fact of 0 is like, all right, I'm the base case. N is 0. The answer for 0 factorial is 1. I will return that back to whoever was asking for it, which was fact of 1. And now it's popping itself off the stack. I really should be deleting this, erasing it, but I'll just draw a slash so that you can remember what's going on. And so now we're back in fact of 1. It saw the answer from fact of 0. It got back the correct answer for 0 factorial. It saw 1. It can multiply its 1 by that to return its answer for 1 factorial. 1 times 1 is still 1. And that is the correct answer for 1 factorial. You see how it really is making its way to the base case and building up the right answer with the recursive cases rule? Isn't that lovely? It's so cool and magical. And now we're in fact of 2 again. Fact of 2 is waiting on fact of 1 to complete. It saw the answer. 1 factorial is 1. It got that back. It can multiply its 2 by that and return 2 times 1, 2 for its answer, which is the correct factorial of 2. And now we're back in fact of 3. Who is waiting on fact of 2? You can multiply its 3 by the 2 it's got back to make 6. Return that back to whoever called it, and that is the correct answer for factorial of 3. And now factorial 4 is the one we're back in. It was waiting on fact of 3 to multiply its 4 by fact of 3's answer, which was 6. It can multiply its 4 by 6 now to get 24. Give that back to whoever called it as the correct answer for the factorial of 4. Beautiful. And then finally, we're back in the original call, fact of 5. It was waiting so patiently on that smaller factorial, fact of 4. It took a long time to compute, had some people to ask smaller and smaller problems too, but eventually it got its answer back. We see 24 back as the factorial of 4. That is the correct answer returned back to us. Our job for factorial of 5 is to multiply our 5 times whatever the factorial of 4 was. And so we've got the 24, we've got the 5, multiply them up to make 120. And that's the final thing that we need to give back as our answer, which is the correct answer for the factorial of 5. And so even though it kind of seems like wishful thinking to make this smaller call and just to assume it's going to work, I hope you kind of see why it will work. It will make its way to the base case, and it will build up the answer. Always will get the smaller answer correctly, as long as we keep building up the bigger answer for the next guy, Okay? So that's factorial in a nutshell. That's a good starter example to refresh our minds about recursion. When we come back next time, I will do an example on trees where we'll count the number of leaves in a tree. So I would, I guess, encourage you to try this yourself. It's going to be a recursive problem. Like, make a tree. Doesn't have to be a BST, just any arbitrary tree. And count the number of leaves in it. And it is a recursive problem. See if you can figure out the base case and the recursive case before I show it to you next time. All right? And remember that you can just make that smaller call and assume that it works. And it really will work as long as you got a correct base case and you're using that smaller answer to correctly build up the bigger answer. All right? So, yeah, that's where I want to stop with the review today. We will come back next time and do the second half of it. So I will see you all then.